Okay, so now all the rest of these slides are going to all be on you try it problems that are from chapter 19 in general. So there's going to be a lot of different material. So which of the following reactions will not produce an aldehyde or a ketone? All right, if we look at the first one, DBA or DBAL H is a reducing agent, and it will take an ester and reduce it down to an aldehyde. And so problem number one will make an aldehyde. If we look at problem number two, or reaction number two, you have PCC and a tertiary alcohol. Remember, tertiary alcohols don't react. So this probably is the one that it will not produce an aldehyde or a ketone, but let's double check on the rest of them. If I go to number three, those are the conditions that would do oxymercuration that produces an enol that then tautomerizes to a ketone there because it's an internal alkyne. So this will produce a ketone. If I look at 4, what would happen is you would get oxidative cleavage. That's ozone followed by zinc and acid. And ozone followed by zinc and acid cleaves a double bond and puts a carbonyl at either end of that double bond. So in the product of this reaction would be both an aldehyde, right here would end up being an aldehyde, and right here would end up being a ketone. So the correct answer to this reaction is right here. The following reaction will occur as shown. Is this correct? Well, if you look, we have a Grignard reagent that's very basic, and we've got a product group there. So no, when this Grignard reagent goes to react with this, before it has a chance to add to the carbonyl, it's going to deprotonate the alcohol. Remember, you'd have to protect that alcohol with trimethylsilane chloride before doing this in order to allow this reaction to go ahead. So no, the Grignard reagent will be protonated by the alcohol, form methane, and then after treatment with acid, this would be reprotonated. So which sequence of reagents will give you the transformation of butanol to alpha hydroxy pentanoic acid? Okay, when you look at this, you can see there are 4 carbons here and 5 there. So you know you're going to be having to add a carbon. So if I look down at the following, you can see there's no carbon being added by this set of reactions. So this cannot produce the product. The rest of them all have cyanide being added in, so yes, it's possible for them to be adding a carbon to the compound. Let's go ahead and look at the remaining ones to see what they actually do. If I look at problem number 1, chromium, of course this would be in a water solution or acid solution, gives us carboxylic acid, so I would get a carboxylic acid here. Lithium aluminum hydride would reduce it back to the alcohol. Hydrogen cyanide would not be able to do anything to this alcohol because it's not, well, I guess you might have an SN2 occur, but the yield would probably be very poor. And then hydrolysis may give you pentanoic acid, but you're definitely not going to have that alcohol group here. Let's look at number 2. PCC would take this to an aldehyde. Treatment with hydrogen cyanide would cause the cyanohydrin to be formed, and then hydrolysis of the cyanohydrin would give you this. Because what does this do? PCC causes this to be an aldehyde. The hydrogen cyanide would put cyanide on here and a hydrogen back on this. Then cyanide, the CN, could be hydrolyzed with acid to form this group. So this would give that product. But let's check with this one to see if this possibly could. If I look at thionyl chloride, that would derivatize this and then do an SN2 to give us a chlorine here. Remember, that was how we were able to get a chlorine, change an alcohol to a primary alcohol to a chlorine. Okay, if I treat with sodium cyanide, we would get SN2. And then I could hydrolyze with acid and heat, and that would give us a carboxylic acid. But I would not have this alcohol group there. So the one that is the correct answer is this one right here. What sequence of reagents would give this? Well, let's just test them all out. Chromic acid would take this down to a carboxylic acid. If I treat with the Grignard reagent, it would just deprotonate the Grignard would deprotonate the carboxylic acid, because remember, acids are protic, and so you would end up with cyclohexane carboxylic acid. You would not have this. Okay, if I look at number 2, PCC would take this to an aldehyde. The Grignard would then take it to this, and following with acid would protonate the negative charge on the alcohol. So yes, this should give it to you, but let's try out the others. If I treat this with the Grignard reagent, you're just going to deprotonate this. Then acid would reprotonate it, and chromic acid would then turn it to cyclohexane carboxylic acid. So no, this one would not work. If I treat with chromic acid, that would take this to the carboxylic acid. A lithium aluminum hydride would then take it back to this alcohol. Treatment with ethyl magnesium bromide would then deprotonate this alcohol, and then treatment with acid would reprotonate it. So you would end up with the starting material after this sequence of reactions. If I take PCC, that would change this to an aldehyde. Lithium aluminum hydride would take it back to the alcohol. Ethyl magnesium bromide would deprotonate this, and then treatment with acid would reprotonate it, so we would end up with the starting material when you got through. So the only one that is going to give you that product is this one. Let's look at what sequence would give us this transformation. Well, let's just go through them one by one. Phenyl magnesium bromide would put a benzene ring here, and then treatment with the alcohol would put a treatment with acid would protonate the alcohol. Methyl magnesium bromide would deprotonate this, and then treatment with this would reprotonate the alcohol. So the only thing that we would get would be the addition of the phenyl group, and we would be missing this extra methyl group. Phenyl magnesium bromide followed by treatment with acid would give us the alcohol, where you would have the phenyl here and an alcohol and just a methyl on the other side. Treatment with PCC would take you to the ketone, that would be acetophenone. Methyl magnesium bromide would then add a methyl group to the alcohol, and you would end up with this after protonation. So this actually would give you that product. Likewise, this one would add a methyl group and make that an alcohol. Treatment with PCC would change it to the ketone. Phenyl magnesium bromide would attack the ketone and give you this after protonation with the acid. So both 2 and 3 would give you the product. Which of the following is the hydrate of a ketone? Well, if I look at this, that's not the hydrate. That's just an alcohol. It has to be a diol to be a hydrate. So I can eliminate these two. It has to be a geminal diol. This is a vicinal diol, and so it cannot be a hydrate if it's a vicinal hydrate. You have to have geminal diols. So if I look at this and this, those both are geminal diols, but this would give you an aldehyde. Only this one would give you a ketone. What's the outcome of this reaction? Well, this is a secondary. I'll let you go ahead and figure this out. This is a secondary amine. Secondary amines are going to give us enamines with a ketone. So let's look around for an enamine. That's an amine. That's an enamine. This is an enamine. That's and this is an intermediate. It's not completed because it still has a positive charge. And this is an enamine. But this enamine and that enamine would revert to an imine. These are not secondary formed by secondary amines. You have to have both phenyl groups on them, so either this or this. This is the intermediate on the way to an enamine, because what happens in the next step is a proton would be removed here, and then you would have the electrons jump to form this. This is the enamine. So the product of this outcome, the outcome of this reaction is this one after the proton is removed by base. So what is the correct functional group assignment for each of these? Well, D is an enamine. So let's find anything that says D is an enamine. So that's going to be 3 and 5. C is going to be an imine. So 3 says C is an imine. B, is that an amine? Yes, that's an amine. 3, you don't know anything about this, but it has to be that it's number 3, so this is an oxime. This is actually from hydroxylamine. Hydroxylamine, when it forms an imine, is called an oxime. Which of the following is an acetal? Well, in an acetal, you have to have no hydroxyl group, only 2 ether functional groups on the same carbon. So let's go through and look. This is actually a hydrate. It cannot be an acetal, because for it to be an acetal, there'd have to be a carbon here and a carbon here. This is a hemiacetal. Carbon here, hydrogen here. It would have to be a carbon here to be an acetal. This isn't an acetal, by the way. That's a ketal. My bad. All right, then we look over here. This is an alpha hydroxy ketone. Okay, so that's not an acetal. This is an alpha methoxy ketone, not an acetal. If I look at this, I can see there's an ether group on this side, and there's an ether group here. This is an acetal. So that